This is a tutorial on graphing polar equations. There are basically two different methods for graphing a polar equation. The first one that we're going to talk about is to simply take our polar equation and convert it into a rectangular equation or an XY equation. Once we do that, hopefully we can look at this rectangular equation and determine what kind of shape the graph is. Here we have the polar equation r is equal to 5. Now if I want to convert this into a xy equation or a rectangular coordinate equation, I have to remember that r squared is equal to x squared plus y squared. Using this, I can square both sides of this equation, and I'll have r squared is equal to 5 squared. Now this r squared, this is equal to x squared plus y squared. So, x squared plus y squared is equal to 5 squared, or 25. This here is the equation of a circle. You may remember the standard form of an equation of a circle as x minus h squared plus y minus k squared is equal to r squared, where h and k are the coordinates of our center and r is the radius. So in this case, our center is at the point 0, 0. And our radius is equal to 5 because this is r squared. So if I want to graph this, I need a coordinate axis. My center is at 0, 0, and then my radius is 5. Really, r is equal to 5. So it doesn't matter what my angle is. If I move 5 away from my origin or my center of my circle, I come to the point on our circle. And once I have enough to see how big my circle is, I can connect the dots. And then this is the graph of r is equal to 5. Or the graph of x squared plus y squared is equal to 25. Again, it doesn't matter what theta is, our r is always equal to 5. Now let's try looking at another equation. Here we have theta is equal to 60 degrees. Now if I want to graph this, I'm first going to convert it to a rectangular equation. Now to do this, I have to remember that the tangent of theta is equal to y over x. And knowing that, I'm going to take the tangent of both sides of this equation. So I'll have the tangent of theta is equal to the tangent of 60 degrees. Now the tangent of 60 degrees, this is the square root of 3. And the tangent of theta is y over x. So I have y over x is equal to the square root of 3. If I multiply both sides by x, I get y is equal to the square root of 3 times x. Well, this is a linear equation. This is in the form y is equal to mx plus b. Here our b is 0, so our y-intercept is 0, and our slope, m, is just the square root of 3, which is about 1.73, approximately. So if I want to graph theta is equal to 60 degrees, I can instead graph y is equal to the square root of 3x. My y-intercept is 0, or the origin, over 1 and up the square root of 3. Connect my dots, and my graph should look something like this. This angle here is theta. It's 60 degrees, and it doesn't matter what r is as I measure along this angle. I'll continue to get different points that are in a line. So if you ever see theta is equal to some number, say a, This is the equation of a line that passes through the origin. Now let's look at another example. Here we have r times the sine of theta is equal to 5. Now we have to remember that y is equal to r times the sine of theta, which means to convert this into an xy equation or a rectangular coordinate equation, we just replace r times the sine of theta with y. So this becomes y is equal to 5. Well, if I want to graph that, that's easy. That's a horizontal line that passes through the point 5, 0. So the graph of r times the sine of theta would look something like this. As our theta gets smaller, our r here is getting bigger. As theta gets larger, our r here is getting smaller. That's why r times the sine of theta is equal to this constant number, and that's how we get this horizontal line from this equation. If we have r times the cosine this time of theta is equal to some number, in this case -4, we just have to remember that x is equal to r times the cosine of theta. Then we can replace r cosine of theta with x, and we'll have x is equal to -4. This is the rectangular equation, or the rectangular coordinate equation, of a vertical line. So this would be the equation of a vertical line passing through -4, 0. Here it doesn't matter what y is, x is always equal to -4. So here is our vertical line, x is equal to -4. As theta approaches 180 degrees, this cosine term approaches -1. You'll also notice here that the r value is equal to 4. So 4 times -1 is how we get this point. As we move our theta away from 180 degrees, our cosine term gets smaller. But our r value here is growing. So r times our cosine value is always equal to this constant number. So that's how you end up with a vertical line in polar coordinates, or in a polar equation. So now let's look at another equation. Here we have r is equal to 4 times the cosine of theta. Now if I want to convert this into rectangular coordinates, or xy equation, again, since I have this single r, I'm going to multiply both sides of this equation by r. If I do that, I'll have r squared is equal to 4r cosine theta. Now I need to remember that r squared is equal to x squared plus y squared, and that x is equal to r cosine theta. If I substitute r squared for x squared plus y squared, and I substitute this r cosine theta for x, we'll end up with x squared plus y squared is equal to 4 times x. Well, I can't exactly see what kind of equation this is. I'm going to move the 4x over by subtracting 4x from both sides. I'll have x squared minus 4x plus y squared is equal to 0. I'm going to complete the square for the x's by adding 4 to both sides. If I do that, I'll end up with x squared minus 4x plus 4 plus y squared is equal to 4. This x squared minus 4x plus 4 is the same as x minus 2 squared plus y squared is equal to 4. This here is the equation of a circle. Remember that the equation of a circle looks like x minus h squared plus y minus k squared is equal to r squared. H and k are the coordinates of our center. So here our center is at 2, 0. And the radius of our circle is 2. Because r squared is equal to 4. If I want to graph this, my center is at 2, 0, which is here. And then I have a radius of 2, so I just need to move units of 2 in a bunch of different directions, connect my dots, and my graph should look something like this. So, r equaling 4 cosine of theta, this is the equation of a circle that's moved off the origin. And it's moved off the origin in the x direction. Realize that x is equal to r cosine of theta. So the fact that there's a cosine here gives us a clue that we're going to move this circle in the x direction. Now here we have the equation r is equal to negative 8 sine theta. Well, I'm thinking that this is probably going to be a circle as well, because the previous one was r is equal to some number times the cosine of theta. But we can check, multiply both sides by r. We'll have r squared is equal to negative 8r sine theta. We have to remember that r squared is equal to x squared plus y squared, and that y is equal to r sine theta. Substitute, we'll have x squared plus y squared is equal to negative 8 times y. Add 8y to both sides, and we'll have x squared plus y squared plus 8y is equal to 0. I'm going to complete the square for the y's by adding 16 to both sides. I'll have x squared plus y squared plus 8y plus 16 is equal to 16. X squared plus 8y plus 16 is a perfect square, so this becomes x squared plus y plus 4 squared is equal to 16. And again, this is the equation of a circle. X minus h squared plus y minus k squared is equal to r squared. Here my h is 0 and my k is a negative 4. So my center is at 0, negative 4. And my r, or my radius, is equal to 4. So if I graph this, I start with my center point at 0, negative 4. And then I have a radius of 4, so I move in 4 in all directions. And I connect my dots. And I end up, as suspected, with an equation of a circle, or a graph of a circle. So r is equal to negative 8 sine theta is an equation of a circle in polar form. And notice that this circle has been shifted in the y direction this time, and our clue that it was shifted in the y direction was this was a sine. And remember, y is equal to r sine theta. Now, if you don't like converting polar equations into rectangular equations, or you have a polar equation that's difficult to turn into a rectangular equation, you can always just graph it by plotting points. Here I have r is equal to 4 minus 3 cosine of theta. So if we're going to do this by plotting points, I'm going to need some theta values, and then I'm going to solve for my r values. Theta values that I'm going to pick are 0, 90 degrees, 180 degrees, 270 degrees. And if I plug these in, the cosine of 0 is 1. 1 times 3 is 3, 4 minus 3 is 1, so our r value then would be 1. The cosine of 90 degrees is 0. 0 times 3 is 0. 4 minus 0 is 4. The cosine of 180 degrees. Well, that's negative 1. Negative 1 times 3 is negative 3. 4 minus a negative 3 is 7. The cosine of 270 degrees, well, that's 0. 0 times 3 is 0. 4 minus 0 is 4. So I've got some points, and I can plot them. Here I have a polar grid. Each ring is another value of r. And then the angle measurements are split up. 0, 1 is right about here. 90 and 4 would be right there. 180 and 7 would be there. And 270 and 4 looks like that. Well, I still can't tell what this really looks like, so I'm going to need a couple more theta values. If this is 90, then this is 45, so I'll try 45 degrees. The cosine of 45 degrees, this is equal to the square root of 2 over 2. Multiply that by 3, and we have r is equal to 4 minus 3 times the square root of 2 over 2. This is approximately 1.88. So if I plot that, that's about here. Next, I'm going to try 135 degrees. The cosine of 135 degrees, that's equal to negative square root of 2 over 2. So r is equal to 4 minus 3 times the negative square root of 2 over 2. And this is approximately 6.12. And I can plot that point. It's about there. And I can kind of see what this is starting to look like. Our shape looks something like this. This is called a lemicon. So by plotting several points, we were able to see what this looks like. And if you couldn't pick it up by the time I had picked 135 degrees for theta, you could just select several more points until this shape came out. So that's how you graph polar equations, by just selecting theta values, plugging them in, and finding r values, and then plotting the points. Now, there are some tests of symmetry when using polar equations. If you can replace theta with negative theta in your equation, and you end up with the same equivalent equation, say r was equal to 5, it doesn't matter what theta is. If you plug in negative theta, this equation is symmetrical with the x-axis. Now, if you can replace theta with pi minus theta and end up with basically the same equation, then you're symmetrical with the y-axis, or the line theta is equal to pi over 2. Now, if you can replace r with negative r and end up with the same equation, then you're symmetrical with respect to the origin, or your pole. However, these tests of symmetry are not always accurate. If any of your equations follows any of these rules, then it is indeed symmetrical. If your equation fails these rules, well, then it might still be symmetrical. You just can't tell using these rules. So instead, let's go over some special graphs of polar equations. If you have the equation theta is equal to a is some number, you end up with a line passing through the pole, and it's a slanted line with this angle A. If you have r times the cosine of theta, and that's equal to some number a, then you have a vertical line, that is some distance a, from the y-axis. If you have r sine of theta is equal to some number a, then you have a horizontal line that's some distance a from the x-axis. If you have the equation r is equal to a, well, that's just a circle. Every point is a distance of a from our pole. If you have the equation r plus or minus 2 times a, remember a is just some number, times the cosine of theta, then you end up with this circle that's been shifted to the right. And you can tell it's shifted to the right or in the x direction because there's a cosine here. Notice that the edge of this circle always passes through our origin or our pole. Same thing if we shift it vertically. We have r is equal to plus or minus 2 times a, which a is our radius of this circle, times the sine of theta. The sine tells us that we're shifting this in the y direction. And again, our circle passes through the pole or the origin. So if you see any of these three types of equations, you know you're dealing with a circle. Now there's several other shapes that are common with polar equations, and you may not have heard of them. One is a cardioid, and if you have r is equal to a plus or minus, now this same number, a, appears again, times cosine of theta or times the sine of theta, you end up with this shape here. It's kind of a bent circle or a circle with an indentation in it. This indentation always touches the pole or our origin. So if you have some number plus or minus that same number times cosine of theta or times sine of theta, this is what you can expect your graph to look like. Now if these numbers are different, a and b, and a is greater than b, then you end up with this lemicon that we saw earlier. If a ends up being smaller than b, then you again end up with a lemicon, but your lemicon has this inner loop. This thing curls in, and you might have another loop inside your lemicon. But again, just memorize this equation. R is equal to a plus or minus b times the cosine of theta. And again, if b is bigger than a, you have a loop. If a is bigger than b, you don't. Another popular shape is the lemniscate. And that's r squared is equal to a squared times the cosine of 2 theta. And it looks like a figure 8. Notice the r is squared and our number, our integer or coefficient for our cosine or our sine term, is also squared. Then you have a 2 theta inside your sine or your cosine term. If you add another petal to this figure 8 shape, you end up with a rose with 3 petals. And now you can drop the square on the r, the square on the a, but now you have a 3 inside the sine or the cosine. If you want to add another petal or have a rose with 4 petals, now you're back to the 2 inside the sine or the cosine, but it's just r times a, where a is some number and then times the sine of 2 theta. So if you can make a chart of these popular shapes and polar equations, you can use these standard equations to get a rough idea of what your graph is going to look like. And that'll help you plot using points. And that completes the tutorial on graphing polar equations.